Thanks for coming out today. So our biomechatronics lab is dedicated to improving quality of life by enhancing the functionality of artificial hands in human-machine systems. And we really think a lot about touch. So you'll see that throughout this talk. We study human grasp and manipulation as inspiration. We design tactile sensors and tactile perception algorithms. And then we leverage sensorized systems to advance robotic grasp and manipulation. But I'm going to put in a shameless plug right now because 'tis the season for faculty hiring. So if you're on the market, please consider checking out UCLA. All of our engineering departments are hiring. We also have some school-wide EDI initiative faculty positions as well. We're also currently in the process of designing and building a 10,000 square foot collaborative robotics space. And we'll have 6 PIs who are all giving up their current labs and moving into this shared space. So we're really excited about that. And about 35% of that space is going to be communal and open to anyone in the engineering school who wants to do something with our fabrication facilities, our motion capture facilities, the robots that we'll have. So we're really excited about this in the next couple of years. I don't have time to talk about what we do on the human side of things, but just to give you a little flavor, we have looked at grip responses to unexpected perturbations, multi-digit coordination, object handover. Some of you may know Eric Chang, who joined my lab at Arizona State back when he was a freshman, and he did his PhD here. We also have been recently getting into eye gaze tracking and using that to infer human intent for activities of daily living. And we've also been doing some work on human haptic search and retrieval and to inspire some of the work that you'll see later on the robotic version. But today, what I'm going to be talking about is really the sense of touch. And I would argue that modern artificial hands may be able to have fast movements and mimic many of the complex movements of the human hand, but I have a little snippet of a video here to kind of start and bookend my talk about the importance of touch.
Correspondent Mike had much of his left arm amputated last year after an accident while on a reporting trip for the NewsHour. He has since been exploring leaps forward for modern prosthetics.
And feel free to adjust it as needed, okay?
A hand without a sense of touch isn't really a hand at all. It's more like a pair of pliers. Watch blindfolded hand amputee Igor Spetic try to pick up some blocks using a prosthetic without a sense of touch. It's not very productive.
That was no sensation.
No sensation.
And so you were just
Going blind.
Just
Literally going blind.
Yeah.
Now watch what happens when the sensory perception is turned on. It's like night and day.
But then when I grab it, if I grab it just right, I feel all 3 fingers. If I grab it right, or 2 fingers. Then I know I have it, and then I'll move over and drop it.
Is it your phantom hand that you're feeling it in, or is...
Oh, it don't feel phantom to me when I grab a block. To me, it does not. It feels like my hand. It feels like something between my 2 fingers that's vibrating.
For Igor, who lost his hand in an industrial accident 4 years ago, something powered by a battery and made of plastic, metal, and silicon can become his hand.
All right, so I'm going to have little snippets of things throughout this talk that'll kind of be formatted like this, where it just gives you some insights into how our lab thinks about touch. And the first one is that touch is useful. And I saw on your robotic seminar series itinerary from this past quarter that you've had previous speakers on touch. So hopefully I'm preaching to the choir here, but touch is useful, whether it's for machines that are working within the human body, are intimately attached to the human body, or working close to the human body, whether at home or on the manufacturing line, or in places where you do not want to put humans in order to keep them safe. So search and rescue, handling of dangerous materials, whether that's decommissioning nuclear sites or looking for explosive ordnance, or in very extreme environments like underwater or in space. And for all of these applications, of course we're going to use all of the sensory data that we have available to us, especially vision, which can be used for planning and also reactive control. However, there are many times when you may not have a direct line of sight, or the hand itself is occluding the object that you're trying to manipulate. You're in the dark, you're behind obstacles or inside containers, or you may have vision, but it's limited. So maybe you're in a wildfire, so there's smoke, or you're in turbid water. And of course, if you're going to work with more complicated materials or objects that are not strictly rigid and for which you may not have a model, there are times when you can use vision to look at the pose or configuration of that item, but from just a straight rope, you cannot tell what is the tension in that rope. And that's something where complementary senses, like tactile sensing and proprioception, become especially useful. So also manipulating deformable thin sheets or even deformable bulk materials, and maybe someday even bulk but animate objects that have their own agency as well. And then of course I had to throw in-hand manipulation, one of the grand challenges for robot grasp and manipulation. So touch is multifaceted, and I'm going to show you a variety of different tactile sensors that we work with. We're agnostic when it comes to tactile sensing. I don't think there's any one piece of technology that rules them all. It really is very application dependent. And I don't think that any of our artificial tactile sensors come close to the beauty of human biological mechanoreceptors, which have very specialized mechanoreceptors spread out in clever ways. So for example, you might have a superficial layer of Meissner corpuscles or Merkel discs, or you have other Pacini and Pacini-like and Ruffini mechanoreceptors in the deep part of the skin. And within each of these layers, you also have mechanoreceptors that respond to transients, so things like vibrations and fast changes, but also to slow, static, sustained strain. And so this is, what I think a lot of people designing tactile sensors aspire to. I don't think we're there yet, but we're working on pieces of it. So I'm going to begin with some of the low-cost DIY types of sensors. Piezoresistive fabric sensors are one type where you have layers, and of course the material itself is responsive to strain. We also have barometer-based sensors, so taking barometers that you can get for your cell phones, but embedding them in an elastomer that you cure within a vacuum. And now when you press on the vacuum, you can measure some change. It's a little bit crude, but you can measure some forces being applied to that bulk material within which the barometers are embedded. If you have a little bit more access to specialized equipment, you can do microfluidic tactile sensor skins. This is a collaboration with Jonathan Posner. We were next door office neighbors at Arizona State, and now he's up at University of Washington. And his team will make sensors, and then we characterize them and adapt them to robots in our lab. But about a decade ago, we started at Arizona State just taking liquid metal and using them as both wire paths and sensing taxels. So where you see these paths crossing over one another, they're not intersecting, they're actually crossing over. And where they pass over one another, you get a little capacitive taxel, or a tactile analog to the pixel. But when we, and this actually only senses normal force because we're just squeezing it along this direction. But if you want to design something for a shear force, we switched from the capacitive approach to a resistive approach. So just think of these as liquid metal strain gauges that you can put in this serpentine direction, which now has a direction of greatest sensitivity, or these circular patterns that allow you to measure normal force equally in all directions. And so if you use both of these patterns, you can use pairs of these serpentine strain gauges to measure shear strain. So if you put your finger down on the armrest near you and you shift your finger left to right and think about where you're feeling the strain in the skin, you probably feel something near your nail bed. And that's exactly what we did here, is we put pairs of these along where a nail bed would be so that you can measure shear in that direction. And then you can imagine if you put another pair here, you'll get shear in that orthogonal direction. But the nice thing is if you can sense from way back here where there's not even contact with an object, it leaves all of this real estate open for the normal taxels where you expect direct contact. So that was the idea behind that design. And more recently, we've taken that design, made it a little bit bigger, and have been working on making it useful underwater, under pressure. So we had to build a lab bench setup to pressurize the system, apply stimuli, and calibrate. We also, like many groups, have been working with camera-based elastomeric tactile sensors. These are all the rage because all the computer vision algorithms can be directly applied to the tactile data, and you can look at the tactile flow. This is a collaboration with Ted Adelson at MIT, who created the gel site. But the idea is that you have a camera embedded within the finger that looks out at the world through this elastomeric finger pad. And if you put an array of dots on the inside, you can track the optical flow and infer local geometry, forces, and torques. And some more recent papers coming out of different groups have now started playing with the transparency of the skin. So if you make the skin more transparent, or even have a way to go from transparent to opaque, you can use this same setup for proximity sensing. So that's a really exciting development. And of course, if you want to go the open source route, Facebook or Meta now has a recipe for the digit, which we have recently been customizing by putting markers on the inside and adapting them to different sensors in our robots in our lab. But the sensor you're going to see throughout most of the rest of the talk is the BioTac, and that's because I worked on it when I was a postdoc with Jerry Loeb at USC. It was funded by the DARPA Revolutionizing Prosthetics program at the time. So it was bio-inspired and intended to go on prosthetic hands. And so it has a rigid core, like the bone in your finger, an elastomeric skin that's inflated away from the core by a conductive fluid. On the surface of the core, I'll have an image later in the talk, but there is an array of electrodes. And if you track how the skin moves toward and bulges away from that array of impedance electrodes, you can infer what's happening to the overall shape of the finger pad. And basically for free, if you tap into this fluid volume with an off-the-shelf pressure sensor that's housed safely in the core, you now have a hydrophone that you can sample slowly to measure a crude measurement of overall fingertip force, or sample up to 2200 hertz and pick up vibrations and vibrations associated with different textures, for example. There's also a thermistor in the front of the fingertip, and you can use the rate of heat conduction away from the finger to infer material properties. So it can be overkill for many of the applications that you might be interested in, but because we already had a bunch of them, we used them on all of our systems, and then we did ablation studies after the fact to test what would happen if you didn't have different types of modalities. How would the performance of your algorithm go down? Okay, so I showed you hardware for transducing mechanical stimuli, or in some cases thermal stimuli, but those are still just an array of numbers that are flowing in real time. So how do we make sense as humans, or even robots, make sense of the data to make decisions? Well, I would say that touch is abstraction, because you need to take those numbers and somehow abstract them to concepts that we can make sense of. Or maybe in the case of reinforcement learning, maybe they're things that we don't fully understand, but that an algorithm can use to improve its performance. So by abstracted features, I'm talking about things like texture, hardness, global shape, local shape. And this classic paper from Lederman and Klasky in the 80s basically defined what's called an exploratory procedure. These are movements that are specifically taken to extract certain types of information. So if I ask you, what is the roughness of the seat that you're sitting in now? You should be imagining what you do to answer that question, and you're likely to rub your finger against the seat, because that is a very typical exploratory procedure when you are seeking information about texture, just as squeezing gives you information about hardness, or hefting something against gravity gives you information about weight. So what we did a little close to a decade ago was we performed exploratory procedures with a sensorized robot, and we looked at edges, edge orientation with respect to the body, local features like bumps, pits of different sizes and shapes. And what we were after was a way for the robot to classify or infer the features that it was sensing so it could decide what it wanted to do next. So just as you reach into your pocket and you're able to find the power button on your cell phone, that's something that we wanted to give, you know, a robot the ability to do without vision, to just feel and know, okay, I'm feeling an edge and I can follow that edge. So that was our first foray into machine learning. We were using things like support vector machines back in the day. Now we use things like convolutional neural networks. This is more recent work on the tactile perception of directionality. And by directionality, I mean you're holding an object and either someone is taking it from you or you're interacting with the environment and you can feel through the object some forces on your fingertip. What is the direction of that force? That's what this algorithm will tell you. And so instead of moving an object with respect to the fingertips, we just reversed it for all of our data collection to move the fingertips relative to the object. And you'll see as we do this that you can actually see the finger pad changing shape. And so we do this thousands of times, collect a bunch of training data. And this is the finger core, the biotech core without the skin. So you can see this array of electrodes. We roughly know the location of these, and we only have 19 of them. And so in order to apply computer vision type approaches, we use interpolation to create a manifold. And what's on the z-axis here is the change in electrode impedance. So when that change increases and goes positive, we know that the skin is getting compressed toward the core of the finger. If it goes negative, we know the skin's bulging away. And then we can turn that into a grayscale image where the intensity refers to the change in impedance over that particular region of the finger pad. And then, of course, if you do that for a bunch of different directions, you can see that there are patterns here, and so our convolutional neural networks are able to figure that out. So this is an example of the real-time playing of the policy or the model that's learned. So purposely, we had the robot grasp the object, but only release when it was the appropriate context, which is when someone's pulling the object away from the robot. When the line points away from the palm is when the robot will release. And the sensitivity of this is something that you could adjust per your application. This is showing interactions with the environment. So as the relative upward movement of the glass is sensed when the object's being placed, again without vision, the robot can respond appropriately to release the glass. But one of the things that we've been working on most recently that's, I think, kind of fun and has been surprising in terms of the things that we've been discovering is putting tactile sensors in granular media. Because you've seen robots that are digging through, walking across, running across granular media, but they don't typically have tactile sensors. And we were funded by the Office of Naval Research to look for buried objects that might be fragile, or you may not want to interact with them directly or do it very carefully. And so one of the things that we thought was going to be a liability and really annoying is the fact that granular media, the particles, can act like fluids or solids depending on how they're packed and how you're intruding upon them. So if you're intruding and dragging your finger through, there will be some particles ahead of you that freely move, kind of like a liquid. But at some point, if that wedge of particles that's moving ahead, we call it the soil failure wedge in the literature. If that wedge tip hits something that's buried, what is created is this chain of particles, a force chain, that will now push back on your finger even though you're not directly touching the object. And what we thought was that, well, this kind of gives our tactile sensor in granular media proximity sensor-like capabilities. So there's a kind of nice parallel between using tactile sensors in granular media with jamming to traditional SLAM approaches where you're using a proximity sensor to map something out. And that was our approach here. So what you're going to see is in this video, the little white dots are the pixels that are changing, and there's going to be a little soil failure region here that moves ahead of the finger. And up in the upper right-hand corner, just know that those are two measurements of roughly the force or the torque on the fingertip. And you'll see that there will be an increase in the force on the fingertip when that soil failure wedge hits this buried object, but the fingertip has not yet reached it. So this is the soil moving ahead of the finger. And around there, we start to see an increase because of that granular media jamming. So if you know or can characterize the properties of the granular media, you can use that to reduce uncertainty in the map that you're building of the buried object. So that's what we did. We're leveraging this transition from free movement to some jamming state. We have a different paper in the works that gets more into granular media jamming with different types of materials, but for this project we used a heterogeneous sand mixture with pebbles and things, and this shows how we can turn this data along with exploratory movements into a Bayesian Hilbert map that tells us about occupancy. So you'll see one exploratory movement from that hand, and that's what we infer from that one movement. Then we have a second one. And with each increase or update in this map, you can think about how to plan the next exploratory movement to reduce the uncertainty in your current map. And after about, I think, 7 movements here, we're able to have a decent occupancy map of the object that we then uncovered to show where it was. But of course, touch is very expensive. So if anyone here collects tactile sensor data, you'll know it takes a lot of effort to get the robot hardware up and running, to program it, to collect thousands of trials of data. Sometimes the sensors can break or wear out. The BioTac that I showed has fingerprints on the skin to amplify vibration, and you will wear out the fingerprints. That's a consumable that you have to replace. So touch is very expensive. I cannot go online and download millions of images to perform data mining with. I actually have to collect the data. So I have a couple examples here of projects where we wanted to demonstrate the ability for the robot to learn a hard-to-code skill. And in this case, we're closing a Ziploc bag, but you can think of it as a functional contour following task, where both the tactile sensor and the object being manipulated is deformable, and we don't have good models for them. I think now there's a better model of the BioTac out there, but it's still not an analytical model. It's yes, with the BioTac model, we can model the deformation of the finger pad, but we don't really have a good model for the electrical phenomenon happening within the pad with respect to the impedance electrodes. So for that, you can bridge that gap with actual tactile sensor data and neural networks, and that's what the literature has done. So here we have set up a camera to track the motion of the fingers relative to this zipper. We do that to automate the learning process, but once the policy is learned, we can turn that off and it'll work. So this is just demonstrating what would happen if you tried naive linear trajectories relative to a linear zipper that you may be able to view with computer vision, but at some point the finger will probably fall off of the zipper unless you make corrective movements because of the way that the bag will deform. So what we did, this was our first foray into reinforcement learning, so we took a very simple primitive approach and we said, okay, what are the different states and rewards? Well, we'll have 3 states, low, center, and high, and ideally you keep that sweet spot of the finger pad aligned with the zipper, because otherwise you're going to fall off the zipper, right? Either too low or too high. And let's reward for being in the center. And then this asymmetric set of actions came about after some pilot studies, but these are the 5 actions that the robot can take after it senses its state and whether it got a reward or not. Of course, there's exploration and exploitation happening at the same time. So what we did in this project was to show how contextual multi-arm bandits could be used to learn expected rewards throughout exploration in an online way. So you have the fingertip moving. We have up here in the upper left how the impedance electrode values change, whether they're getting squished towards the core or bulging away from the core. We have down here a classification of the state, and then some reward or 0 that goes along with that. And once we learned a policy for this, we demonstrated the learned policy on other types of bags that were not used during training, and these happen to be more flexible. You may have recognized the McMaster car bags in the previous video. These are more soft, flexible ones that you'd find in the kitchen. And we also tried it with different loading conditions, which we had not trained upon. And there's a lot of, we had to speed it up because of the motion planning delay. That wasn't something that the student was very motivated to fix and find with me. That was not the point of the study. So I was happy with this. The other hard to code task that we recently completed with a little more sophisticated reinforcement learning was turning a page in a notebook, which sounds very simple for us, but it's surprising how related your action is to the tactile stimuli that you get. And we can actually pick up on very subtle changes in what's going on at the fingertip, even with just grabbing a piece of paper, which I'll show you in a couple of slides. So we had a Canova arm, BioTac sensors, we had binders here with pages, we threw on motion capture markers because our reward function took into account how the multimodal tactile sensor data diverged from what we called a functional set of data, as well as binder movement. So if the binder moved too much, then we would call that an aggressive movement. So I'll show you here these three different classes of page flipping behaviors that we use to demonstrate reinforcement learning in a model-free way using tactile sensor data. And we had to make up some kind of ideal, functional ideal, so we decided that it would be this one where it's a semicircular trajectory. Just imagine the fingertips kind of following a half circle. And then we had other undesired page flipping behaviors. One is with page warping and snapping, so you can imagine if there's a radius for that semicircular trajectory and you decrease that radius, now you're going to force the page to warp. And then when it gets turned over here, you'll see it snap. And we can actually pick up the transient of the snap with our BioTac. And then if you imagine that now that radius is increased, now you're pulling too much and too hard, and you'll get the binder movement that we penalize for in our reward function. Of all these three cases, I think the one that's most interesting to watch is the page warping and snapping. So there's the warping, there's the snap. And so at the end of the day, the pages always get turned, but they're turned in different ways. And in this example, we were trying to show that the tactile sensory data changes in a different way. So don't bother yourselves with the intricacies of the data, but I just wanted to show you that we have different responses for the top finger and the bottom finger. They experience different things. Within each of the fingers, depending on where you are on the finger, the electrodes experience different things. And then depending on the page flipping behavior, that you get different responses. So the aggressive trajectories are shown in red. You can see these little spikes for the blue with the snapping of the pages. And we were trying to get the robot to learn, even if starting with a suboptimal type of trajectory, can it learn to adjust its motion rollout according to tactile sensor data only to get back to something that is more ideal in our case. And so we were able to do that. And not only were we able to do that for a nominal trajectory, but then we showed that we could adapt a learned nominal trajectory to different contexts. So if you learned on small pages and then were told to adapt to a different context, like large pages or vice versa, you would necessarily have to change the radius of your trajectory, and the robot was able to do that using tactile sensor data. So the left column is the first policy update, and by the time we were happy with the performance, that's the right column. So even starting with a suboptimal movement after a certain number of policy updates, using the tactile sensor data, we could get to something that we consider to be ideal. All right. So the next point I have, just a couple slides, is that touch is shareable. So if you can collect the tactile sensor data, you can send that to somebody. You could use it for the robot to make its own semi-autonomous decisions, but if you have a haptic display, then you can send that to a remote operator of a robot. So this is me at ICRA attempting to bimanually control this setup to manipulate this little block, and I'm doing it remotely, and I'm really trying to use my visual feedback, but at times it was occluded, so the touch helped a little bit there. But the point is that if you can sense what's going on at a remote robot location, you can convey that back and share it with someone else. So this is the video that I meant to bookend and pair with the one I showed before. Again, this is a follow-up for Dustin Tyler's lab at Case Western Reserve University, with whom we have a new collaboration.
Presswood lost his arm in a workplace accident in 2012 and is also a participant in Tyler's study. He too had surgery connecting his nerves to sensors in the fingertips of a sophisticated prosthetic limb.
Basically, they've mapped where if they put this electrical signal to this contact on the nerve cuff, then that makes me feel a pinprick in my index finger.
But he doesn't even have to wear it to get that feeling.
The fact it's attached to his arm is actually kind of arbitrary. We can put the prosthesis anywhere in the world, and he would still feel like his hand.
Prestwood is trying out the idea with his prosthetic arm mounted across Tyler's lab.
And so now we can extend his capability. We can essentially amplify the person by taking that sense of connection, the sense of touch, and putting it on any machine in any part of the world and bring it back to your nervous system. And then I can connect it to devices that can do far more than my weak biologic system.
All right, so this video and with the block stacking task, you can think that, you can notice that it's a lot about functional tasks. Did I get the job done? Am I getting the right type of feedback to appropriately adjust my grasp and manipulate the object? But the last thing I want to tell you about touch is something that I've been thinking more recently, and that is touch is connection. Right? So affective touch is a field that's already existed. It's only I'm just beginning to get into that area along with Dustin Tyler, and it's a change for me in the way that I think, because I've always been thinking so much in terms of did I get the zipper closed, did I turn the page and all that, but there are other aspects to touch that are about the social connection, whether you're trying to connect with a little one or a bigger loved one, right? And you know, because of COVID and social distancing, the fact that we weren't allowed to hug for a long time, even at the ICRA conference, you had little badges that were, you know, are you okay to shake? Are you shake hands? Are you okay to elbow bump? Or you're just, you know, you're not ready to interact that way. So I think we're still moving through this, but even after the pandemic is over, there are going to be populations of individuals who still, for various reasons, maybe they are medically vulnerable, high risk for infection, are not going to be able to get back out into the world. And that's where having a robot avatar, for example, can help reconnect people to these community activities. So because of COVID and everything, Cynthia Gorney actually interviewed many labs around the world, and Dustin and I were very lucky to be included in this cover story on the power of touch. But it really focuses on touch from a social perspective. So a little bit more about what we're doing with Dustin. He launched the Human Fusions Institute, which is aimed at directly connecting human and robot experiences using what they call neuroreality to enable humans to be physically in one place and experientially in another, ultimately to enable embodiment. And I'm not saying that you know, teleoperation, telepresence, teleexistence is anything new. That has, you know, teleexistence was created, I think, back in the 80s in Japan. But I think there's a renewed interest. And I think that the interest is starting to go beyond teleoperation from a functional perspective to embodiment, where it's about enhancing not only the operator's social experience, but the experience of the people that operator is interacting with. And I think there's a lot to be explored there. So we threw our hat into the ANA Avatar X Prize competition, and we only had, I think, 6 to 9 months to put something together. So we went a totally different way from the groups that you may have viewed either in person or via live stream at the finals about a week ago. The typical approach is to get very large robotic arms, have 2 of them so you can do bimanual things, mount them to a mobile base and have this gigantic mobile manipulator, and maybe have an exact replica that an operator will remotely wear and move, and then the avatar mimics. We went a completely opposite way because we wanted to do something that would really focus on the operator's experience, and so and also safety. So this is the stretch robot from Hello Robot. It purposely has a very small footprint. It's very lightweight. It's meant to go in homes and be used by individuals with impairment. It does not have a serial linkage arm. It has more of a gantry style arm. And we took off the passive suction cup gripper style end effector and put on this sensorized prosthetic hand that Dustin already had access to. And then we took the Intel RealSense, the RGB D camera, and we slapped a Z Mini camera right over the top because we weren't going to do anything automated. We just wanted to send binocular vision directly back to the operator, who is in Cleveland. And so the operator system had an electro-tactile haptic display and was wearing a commercially available headset for audio and visual feedback. And the goal was, as usual, for many teleoperation approaches, immersion, seamless embodiment, intuitive controls, multimodal feedback. But again, we were really focused on what the operator would experience, so we spent a lot of time on training the operator, and even just having the operator tell them to close their eyes. We engage them with the remote system, and then we say, open your eyes, welcome, you're in Los Angeles now, and having this training regime where, when someone is operating a robot, I think it's different than someone embodying a robot, where now you need to think about peripersonal space and etiquette. I actually startled the National Geographic journalist when she was in Cleveland. She was operating the robot in our lab, and I thought I was being friendly, and I popped right in front of the camera and I waved and said, "Hi, Cynthia," and it startled her because she didn't have the field of view. She wasn't expecting me to do that, and you would never do that to someone who was right in front of you. You'll just jump out in front of them, but I had not thought of her as in that way. And so I think both from the operator's perspective and the other interactors, there are some social etiquette things that still need to be worked out if we're really going to head towards embodiment as opposed to just functional teleoperation. So we focused on the 2 things that we thought were most important for the operator, which are the ability to have binocular vision and control where you're looking, as if in an egocentric way, and then having some tactile sensation on the hand. These are not the greatest tactile sensors, but they are cheap and already built into the hand, and it's surprising, I was surprised when I tried the system, that even a very simplistic approach to tactile sensing, when you have visual tactile synchrony, it's actually a very powerful combination. So I have one more funny anecdote you might enjoy, which is we were setting up this demo for a VIP visitor, and I wanted to make sure I tested it. And when I tested it, and I closed my eyes, they said, "You're engaged." I opened my eyes. I saw myself from behind, and it was really weird. It was kind of like the Hermione Granger experience, if you know Harry Potter, where you see yourself from this third-person perspective in a way that you shouldn't normally. And so after that, I told my student, please make sure that the VIP faces that way and the robot faces that way, because it's already difficult for someone who's not used to this technology to interact with it, let alone have kind of a meta experience on top of that. And then on the local operator side, what we called Cleveland, this is the headset. We used hand tracking built into the headset. Again, we were going for something easily scalable, low cost, very deployable, so we didn't have motion capture systems. We didn't have fancy 7 degree of freedom arms to capture all the movements. We threw a white glove on for contrast and tracked the hand that way. And yeah, we were pleased. We made it to semifinals and have established a productive collaboration. So the last thing I want to leave you with are just things that I think are unsolved challenges if you're looking for new things to inspire you. Things that I think are exciting directions, not only in robotics related to touch, but also what I think is going to be a new field of social physical human-robot interactions. Right? We've had physical human-robot interactions, social HRI, but social and physical, I think, is up and coming. So I mentioned this a little earlier in my talk, but combining proximity and tactile sensing, I think, is something that is underexplored, and there's a lot to be learned there. There were previously other attempts to put cameras in the palms of hands and things like that, so that as you're approaching an object with your hand open, you could adjust your hand placement relative to the object and then close the hand. But I think having proximity sensing wherever you put tactile sensing would be really exciting. Also sim to real for tactile sensing. So this goes back to the touch is expensive part. Unless you have a tactile sensor for which you have a nice analytical model, it's really difficult to predict the sensory effect of an action that you take. And there's this action perception loop, right? You perform an action to perceive something. Once you perceive something, you can determine your next action. And I think, perceiving something and then determining either the action that got you there or the action that you should take after is difficult. So if we had sim to real for tactile sensing, that might enable more reinforcement learning to happen in simulation and then directly transfer to hardware. Talking about social physical interactions, one good example is HuggyBot, which was created by Alexis Block. She's a postdoc in my lab, and she had numerous PhD advisors, one of whom is Catherine Kuchenbecker. And she created this before the pandemic, and received some negative comments about it when she first started. And now it's actually finally being recognized as something valuable now that the whole world has endured the pandemic. Just the lack of physical interaction between people, I think, and that social connection that you have just from a hug or a congratulatory pat on the back or a comforting stroke on the arm. These are all part of the social physical interaction field. And an example I heard about recently is a cafe in Japan that enables impaired individuals to re-enter the workforce by logging in from home and embodying this avatar that can serve you in a restaurant. And I think that has both the functional and the social component to it. What I did not put in pictures on this slide is shown on the bottom. Large area tactile sensing. How do we go from tactile sensors that are just on fingertips, maybe on palms, to everywhere? And once we start scaling up that way, are we going to need different types of processing approaches? So there are some groups that have been working on neuromorphic hardware for some time, but they're starting to get a lot of attention from funding agencies now for event-based neuromorphic tactile sensing, so that you're not wasting your power, your processing effort on sensing a full body's worth of data when nothing's happening. You're only paying attention to it when something interesting is happening that will make you think about it and maybe respond. Right? So I thank all of my collaborators, the students that do all of the work, and our funding agencies, and thank you for your attention and happy to take questions.
I can pass the microphone around if there are some questions.
Thanks for the really interesting talk. You've shown a lot of slides and videos about humans with prosthetics recovering their sense of touch through sensors. I'm curious how the interfacing between the sensor device and human neural systems actually work.
Yeah, I would say it depends on whether you're going invasive or non-invasive. If you're going invasive, one of the older approaches, and it's still used, is to go directly to the somatosensory cortex, brain-machine interfaces. There are some groups that want to leverage all of the circuitry that is still intact farther down the stream, which is why researchers like Dustin Tyler use peripheral nerve stimulation, and they have cuff electrodes that will have different stimulation patterns, and that again is an art. The bridge between the tactile sensor numbers that are streaming in and what you actually use to stimulate is where the bioengineering and the engineering choices have to be made. Because I've given talks like this before where people would say, well, why would you ever want to convey to an individual with limb loss the orientation of an edge? Like, of course, you wouldn't, right? Why would I tell them, oh, that you're touching an edge, and by the way, it's 10 degrees from the long axis of your finger. I think that's something that you might do for a semi-autonomous robot, but for someone who has agency, you might get more bang for your buck by just streaming in the raw data. Maybe having as much of a one-to-one mapping or some kind of filtration from the tactile sensor that is not biological at all to some set of patterns, and hopefully the patient can learn that mapping. And everyone's going to have to learn a different mapping. It's a different embodiment, and no one has the same reaction when you stimulate them in the same place. It's very subject-specific.
I see. Thank you.
Mm-hmm. And I don't think it's natural. I think that a lot of people say, are you really restoring natural sensation? And I don't think my collaborators claim that they are. It's just additional information that was lost, but now when you give them some information about their physical interaction, it helps their performance. Maybe it helps with their sense of connection to someone. That's what we're after.
Hi, I have a question about this last remark that you made about the neuromorphic tactile sensing. Tactile sensing has not come into the picture.
Yes.
So just if you can elaborate a little bit.
Yeah, well,
about
I'm
that.
brand new to this too, and I'm trying to drink from the fire hose because my understanding is the event-based neuromorphic approach has been applied to vision, right? And so there are groups, I'm looking forward to starting collaboration with Chiara Bartolozzi in Italy, and we want to try those techniques on tactile data. And so what I'm learning are hard neuromorphic approaches and soft neuromorphic approaches. And I think for our lab and the collaborations in the short term, because we don't do any of that hardware design, we're going to do the soft neuromorphic approach where you collect the data and then you interpolate and assume you have way more samples than you do. And then what's currently over my head but I want to learn are spiking neural networks. That's something that my group has not done yet, but we would have to learn in order to apply these neuromorphic approaches.
Hi, thanks for the talk. I had a question about calibration for these tactile sensors.
Mm-hmm.
How painful is it generally to calibrate two tactile sensors with each
Painful.
other? Yeah.
Because especially with the handcrafted ones, they're exactly that. They're handcrafted. They're not commercially available devices that you could just send to the vendor and they just hit the go and then send you back a little calibration matrix. For us, because our tactile sensors, you'll notice, are pretty much all deformable, everyone's a little bit different. So calibration means applying a known set of stimuli, recording the numbers that come out of that, and building some usually nonlinear model to link the two.
I see.
Yeah.
And you usually have that ground truth with you?
Yes, so it's important. Well, it depends on what you care about. So some people care about actual numbers, like was it 0.1 newtons or was it 0.2 newtons? In that case, you need to mount your sensor to something with an actual calibrated load cell beneath it, like a 6 degree of freedom load cell, so you can report those things. If you do not care about absolute magnitudes, but you care about relative changes, then that's really all that matters. And calibration is essentially baselining before any contact, and then having some known stimuli and looking at the ranges of changes. And going back to the neuromorphic approach, maybe you have, for greater intensity of magnitude or greater change in like an impedance electrode resistance value, you have a higher frequency of firing or something. Depends on the slow adapting or fast adapting type of mechanoreceptor you're trying to emulate.
Thank you.
Mm-hmm. That's the calibration is the unsexy stuff that students have to do and never makes it into a publication.
If not, all right. Well, thank you, and thanks again to the speaker. And oh, turn off the mic.
I actually have one more.
Of course.
Oh, thank you.
Yep.
Just a small question on the liquid metal-based capacitive sensor. I think that's the one on the top right. So it looks like I guess I'm curious, in such design, the wires would also be basically sensors. So do you have thoughts on like shielding, or how do you deal with like?
Yeah, we haven't had too much many problems with interference in that sense. I think because if you actually stretch and twist these things, the amount of change of capacitance or resistance over the taxel that you care about is much smaller than what you care about when you actually have a stimulus. So we haven't had that trouble with this yet. You're talking about the bits of like the bits of wire that are out here possibly acting like an antenna?
Mm-hmm.
Yeah. Yeah, I think if we were looking at something that was really sensitive, that would probably be a problem. But for us, looking at maybe 0.1 newtons for very light touch, or in the case of the underwater example, 200 newtons, that's not going to be an issue.
I see.
Yeah.
Thank you.
The thing that is an issue that everyone glosses over, but since you're interested, the hardest part about this is the bridge from the liquid metal wire to the rigid wire that has to go to the DAC board. That is what rips out all the time. So that's why this sensor actually has no rigid wires shown, because we've played with it so much that they've popped out. But that interface, if someone can solve that liquid soft to rigid transition, that would be a game changer.
I have my own troubles with those stuff. Yeah, I totally feel you.
All right. Thank you again.
Thank you.
And we'll conclude.